All right. Hello again. This is the second part of chapter 4. I hope you're doing well. Let's get started on chapter 4. And we are going to talk about linear approximations and differentials in this section. Now, the idea is very simple. Let me explain the idea quickly. If we have a function and we are interested in finding, so let's see, this is f of a. Now suppose we want to find a plus dx, a little bit to the right of a value close to a. Now, this linear approximation idea says that at a, if you draw the tangent line at a, right? That's the tangent line at A. If you zoom in right here, what you're going to see is really a straight line, right? So the curve is over here, but as you zoom in, close to that A, you can think of the function as actually the tangent line, right? So we know the function is like f of x equals to some value, let's say x squared plus 1, right? But the equation of the tangent line to a is given by what? Y minus f of a equals to f prime of a times x minus a, right? Now here, if we assume that f of x is the same as the straight line, the tangent line, then think of it, this is like y equals to x squared plus 1. This y equals to, if you move the f of a to the other side, would be just f of a plus f prime of a times what? Times x minus a. So this is the tangent line equation, and this is the function equation. So in order to find the function value at a plus dx, right? To do that, to find the function value at a plus dx, we are going to substitute a plus dx in here for x. So we're going to use, if you think of like right at that point right there, there is a distance here, which is the y value if you substitute a plus dx in the tangent line, and there is a distance a little bit higher up here. So that distance versus this distance. So we're going to approximate this bigger distance using this smaller one from the tangent line. That's the idea. So let me explain it a little bit more with a better drawing. So you see, so we want to find the f of a plus dx or delta x. Dx and delta x are the same. So if we go up to the tangent line and find that y value, so that distance here would be the distance that is the y coordinate of this point on tangent line, right? But that distance right here is actually the y coordinate on the function when x is a plus delta x. So as I described, the equation of the tangent line turns into y equals to f of a plus f prime of a times x minus a. Now we're going to call this the linearization of this function. That means when you zoom in, you can just consider this function to be the tangent line at that point. So if there are points close to a, around a, here of course we zoom in to understand what's going on, but usually this a plus delta x is really close to a, it's right there. So the difference between tangent line and the function are really small. It's really small. Okay, so for a small delta x, f of a plus delta x can be found by using the tangent line And we call that the linearization of the function, L of x. So instead of y, we call it L of x. All right, now, when we substitute a plus delta x here, a and a get canceled. So what we get is basically that. And that is a way to approximate function values using the tangent line. It's called tangent line approximation or just linearization of this function. This expression that we get is a linearization of this function at x, right? Of course, x here could be any value close to a, right? The linearization is done at a because we have to find the tangent line at a, right? Okay, so that's the idea. So let's do it. It says find the linearization for the function f of x equals to square root of x at x equals to 9. Then use it to estimate the square root of 9.1. So as you see here, here is, so let me do this quickly with our program called GeoGebra, right? So let's do that. So once we do it, so what I'm going to do, I'm going to put f of x equals to square root of x, right? And then I'm going to go to point, let's say I'm going to put a is a point, and that point is 9, and f at 9, right? So I didn't put equal to, let me fix that. So equals to, that's the point right there. Then I'm going to tangent to that point. So here we go. Let's do the tangent at this point and at that function, right? All right, now if I zoom in, notice right away, you see around 9, the function and the tangent line are really close. But if you zoom in, they're even closer, you see? I could change this maybe color of the line to red. So let me change it to red so we can tell the difference. So you see now we don't even see any black region, right? It's all red. When we get closer and closer, and you zoom in, the function values and the tangent line values are basically very close, right? As I zoom out, you see there are different, right? You see that? If I zoom out, you see there's two different functions here, right? So that's the idea. That's why it's called linearization. That means you're making the function to be a straight line. You linearize it. You making the function a straight line. Okay, so how do we do it? Well, what we do, we're going to find the equation of the tangent line to f of x at 9. And that's easy to do. It's just what? Y minus f of 9 equals to f prime at 9, right? That's prime, times what? X minus 9, that's it. What is f of 9? 3, right? So f of 9 is 3. Let me fix this, the mess I made here. So that's f prime, and that's equal to. So y minus what? Minus 3, right? Because f of 9 is what? Is 3. Equals to, what's f prime? Well, the derivative of square root of something is 1 over 2 square root of something. And the derivative at 9 is just 1 over 2 square root of 9, which is 1 over 6 times x minus 9. Now, all we have to do is solve for y. So it's going to be 1 over 3 plus 1 over 6 times x minus 9, right? Now we're going to call this what? L of x. So L of x is nothing but what? but this, which is given right here, a better looking handwriting right there. I mean types. Okay, so the linearization of this function at what? At x equals to 9 is given by what? By this function. Now, if you want to approximate the square root of a number close to 9, right, let's say this is 9, so that's the point. So you draw the tangent line, and then you find, let's say 9.1 is over here somewhere. So the height from here to here is the approximation that we make for actual value, which is actually that much, right? So that's the idea. Now, we want to put 9.1 in here for x. So f of 9.1 is the square root of 9.1 is approximately equal to what? Equal to that. Which, if you use a calculator to do it, you see it's kind of close, right? It would be 3 plus that, so it's 3.016. And that's what the value of the calculator gives us, right? So it's a pretty good approximation. And think about it, when we didn't have calculators, like, 1970s, for centuries, people had to use these methods. Even the calculators are programmed to use similar methods to approximate the values of functions. Okay, here's another one. It says find the linearization for sine x at x equal to pi over 3. Well, we do the same thing, right? And then use it to find the sine of 62 degrees. So again, we find the equation of the tangent line, which is what? Which is a y. Instead of y, we could just put what? We have a formula for L of x now, right? You don't have to start with the equation of the tangent line. We have an equation, we get a formula. This is the y in the tangent line, which we call it L of x, right? So that's the formula for L of x. A here is pi over 3. So we're going to have to find f of pi over 3. What's f of pi over 3? Is sine of 60 degrees. Sine of 60 is square root of 3 over 2. And then f prime, what's f prime of sine? The derivative is cosine. What's f prime at pi over 3? Cosine pi over 3 is 1/2. So we put 1/2 here for f prime. And then x minus a is pi over 3. Here, this is the linearization of sine at what? At pi over 3. So if you're close to angles close to what? If you want to find the function value sine of angles close to 60 degrees, like, 62.1, 60.1, 61, 62, close to 60, right? So here's 60, 62 is close to it, right? So to find it, we can use this. So put just 62 degrees here, and this approximately equals to this. Now, since this is in radian, we're going to change what? Change 62 degrees to radian. To go from degrees to radian, you have to multiply by pi over 180. So 62 times pi over 180, that's in radian. And we substitute in here for x and use a calculator, right? We could just use a calculator. This is the value. And the calculator gives 0.8829. And look, it's pretty close to that value, right? It's a pretty good approximation. All right. Now we're going to relate the linearization to something called differentials in calculus. Now you know that we use dy dx as a notation, Leibniz notation for f prime, right? So f prime of x is dy dx, right? That's what that is. Now, using this, we can actually separate these and think of dx as a variable. Remember when we wanted to find the slope of a tangent, we went to the right of it and then found the secant line and let the delta x approach. Let's say this is a plus delta x. We say let delta x approach 0, so this point approach this point, and this point approaches this point, right? And this way we can actually get an estimate for the slope of the tangent line. To do that, we get the f prime, of course. But if we think of dx as a number that can actually change, so as we are getting closer and closer to a and changing dx, then dy actually changes, right? Which is the slope of the, which is, if you separate it here, dy is the slope of the tangent line times that dx, right, if you cross multiply. So we're going to think of this as a function of, right, dx. And of course, f prime also changes here, right? So dy and dx are called differentials, right? And we can divide both sides, of course, by dx. Now we can think of what? Think of the Leibniz notation or differential form of derivative. So, so let dx be an independent variable that can be assigned any non-zero real number, and define dependent variable dy this way, right? So now these two are differentials, and we can think of them as, let's do an example. So suppose you have f of x equals to cosine x, and you are at point x equal to 3, and you're about 0.1 to the right or to the left of 3. If you're 0.1 to the left and right of 3, then dy values are going to be between what number and what number, right? So here you go. So how do we find dy? Well, we have a formula. dy is f prime times dx. F prime at 3, right? So f prime at 3 is, we substitute 3 for x here. For x here in the f prime. So it would be a negative, whatever sine 3 is, we don't have to actually find it, we just leave it in the formula. So negative sine 3, and remember this is not 3 degrees, it's 3 radians, right? And then times what? dx, which is 0.1, right? So as on the x-axis, if you're at 3 here, and you are within 0.1 of 3, that means 2.9 and 3.1. Then on the y-axis, this is, if this is y value at 3, right? Then the y values will be what? Will be this much away from this point and this much below it, right? So that would be the range of what? The y values for the range of x values of input over here for this function, cosine x, right? So if this number here is cosine 3, right, then would be cosine 3 plus and minus what? This much. So that's the idea. And this is very useful in error analysis, right? So the connection between the tangent line that we talked about, linearization and differentials, is clear here now. So if you think of delta y, right? So if you have a function, and here is, a, and here is a plus delta x, the difference between the y values, f of a plus delta x, and remember delta x and dx are the same, and f of a, difference between these two, right, is delta y, right? So delta y is the difference between f of a plus dx and minus f of a. Again, delta x and dx are the same, right? So we know delta y equals to that. On the other hand, we know the linearization equals to what? F of a plus f prime of a times x minus a, right? Now for a small dx, of course. So that means this right here, f of a plus dx, equals to approximately the same as linearization at a plus dx. That means what? That means f of a plus dx, which is the left side, is approximately equal to this expression here, which is the linearization, right? Now, if we substitute x plus dx for x here, right, what do we get? We get a plus dx minus a and a go away. So what we get is f of a plus dx equals to f of a plus f prime times what? Times dx. So that's f prime at a times dx, right? So that means if I move this f of a to the other side, the difference between these two, which is actually delta y, is approximately equals to that, right? Which is what? Which is f prime of a times dx. But we know this is what? This is dy. So delta y is approximately the same as dy, right? So when we use dy as a function of dx, we are approximating actually delta y here, right? So when we write this, we're approximating delta y by dy using this function. All right, so again, here is a picture. Delta y is the difference between f of a plus dx and f of a. But dy is actually the y-coordinate, the rise on the tangent line, right? On the tangent line, rise over run is the slope of the tangent line, right? And the slope of the tangent line at a is what? Is f prime, right? So the slope of a tangent line at a is dy over dx. And dy is dx times f prime of a. So what we are doing here is we are assuming that delta y is approximately the same as what? As dy. All right. So for a small dx, again, this is true, right? We have to be around a. If we are way over here or way over there, this doesn't hold, right? Because the difference between tangent line and the function gets bigger and bigger. So you have to be around here, right? And that is true. Okay, so this is very useful because think about it. In error analysis, suppose you find the volume of a cube, right? So the volume of a cube, of course, is x to the third power. X is what? The side. And so if you think about the x to the third power function, we don't need the negative part, we just need the positive part. So suppose you measure the side of a cube, and of course the instrument that you use, because of the instrument that you use, you have certain error here, right? So when you measure x, you have some error. We're going to call that error dx. So your x would be plus and minus some error. Now the question is, how is the volume changing? What would be the error in the volume? The error in the volume would be, v would be plus and minus dv, right? So you see dv and dx here are related. And it's a very useful tool in application problems, right? Because in application problems, input has some certain error. We are interested in knowing what the error in the output is. And usually the error is small, so we can use that idea I just described to you, right? Because we are around x, dx is small, so we are around x, so we can use this idea that the volume of the cube changes, stays within plus and minus dv. So we can calculate dv for a given dx, right? So let's first of all calculate delta y and dy just to practice and see the difference. So here, here's a function. Of course, delta y for x equal to 3 and dx equal to 0.1. Delta y is the difference between f of 3.1 and f of 3, right? That's delta y. And we could just use a calculator and do that. We get 0.81. Now, what is dy? Well, dy has a formula. dy is f prime at a times dx. A here is 3, right? So we have to find the derivative of this. What's the derivative? Is 2x plus 2, right? And take the derivative and substitute 3 in it, we get 8. So dy is 8 times dx, which is 0.1. So you see the difference is really small. Our delta y is 0.81 and our dy is 0.8. So we can safely kind of approximate that delta y using dy, right? Now, before I talk about error in calculations, I want to make sure we understand the difference between accuracy and precision. So accuracy has to do whether you hit the target or not. Precision has to do with if you do it again, can you get the same number, right? That's precision. So for example, here, you see these blue dots here in the middle? There you were successful, let's say you did that, you were successful to hit what? To hit the target, and every time you hit it was close actually to the target. So you have good accuracy here because you're close to the target. You have good precision because they're all the same basically place, very close to each other. So this we have high accuracy and high precision here. What about this cross symbol? Well, the cross symbol is around the target too, but every time you hit it, well, it's a little bit further away. So your precision is not that good, but your target is pretty good. So you have good accuracy here and low what precision. Now, what about with this diamond shape right here? How did you do here? Well, you're away from the target, obviously, so accuracy is pretty low, but your precision is good because they're all around the same place. So you have a good precision, but the accuracy is off. And then the triangular shape target, points here, you don't have good accuracy and you don't have good precision, right? So that's the idea of accuracy versus precision. All right, so now the amount of error. If f is differentiable at a, the propagated error delta y is given by approximately dy. Now, what does that mean, propagated? It means that when you have a system and you have a bunch of formulas in the system, when your input is off by dx, this input goes in there inside these formulas and comes out as dy. Now, dx and dy will not be the same because dx is going to propagate in the system and become a big error. We want to prevent that, right? So in application problems, we're interested in calculating this output error basically based on the input. Unfortunately, we do not know the exact value a. So when we measure something, let's say you measure a square side, right? And you get 5.1. How do you know this is the actual answer? We never know. But we can say, okay, we accept that this is the answer plus and minus some error. So instead of calling it exact, we say, no, it's not exact, but it's exact, which we don't know what it is, plus and minus some error, right? And that would be our input. And our output error would be dy, approximately, right? Approximately would be dy would be f prime at a plus dx times dx, right? So we can find the output error based on the input error. Now notice we cannot find this. Why? Because we don't know what the exact value is, right? So we're gonna find what? Find that instead. All right, so here's an example. It says an astronaut using a camera measures the radius of Earth as 4,000 miles with an error of 80 plus and minus 80 miles. Use differentials to estimate the relative and percentage error of using this radius measurement to calculate the volume of Earth, assuming the planet is a perfect sphere. So the radius is accurate to within plus and minus 80 miles. So that means our, let's call here the volume is what? 4/3 pi r to the third. So input variable is the radius r. So we're talking about dr, and we're going to talk about dv, right? So the input error is plus and minus dr, and the output is plus and minus dv. Now, the input has to do with r plus and minus dr, and the output is v plus and minus dv. So here we say, okay, if this is r, right, r is going to be between what? So the answer, the real r that we're looking for, right? So the real r that we're looking for is going to be, which we don't know what it is, right? The real r is going to be between r plus 80 and what? And r minus 80. So that means the number that we find, which is 4,000, is not the real r, but is what? Is either r plus 80 or r minus 80 or something in the middle, right? That's what that is. It's not the actual one, but it's between those two. So now, these are of course DRs, right? And that would be 80 and 80, right? So from here, we know dr has to be between 80 and negative 80, right? From here. And we are given that actually, right? So that's our dr. All right, now the volume equals to that. What is dv? Well, dv would be v prime at r times dr, right? That's what dv is. So this is v prime at r times what? Times dr. But what's v prime? V prime is 3 times 4/3 pi r squared, which is 4 pi r squared. So that part of it is just v prime and this dr. All right. So using the measured radius of 4,000 miles, we can find dv is going to be what? dv is going to be, well, this is the formula for dv. And dr can be either 80 or negative 80. So our dv would be between those two numbers, right? So it's going to be basically v of 4,000 times, v prime of 4,000 times dr. And then here also v prime of 4,000 times dr. But of course this dr is positive and negative here. That's what we get. So that's our dv. And we can calculate it. Then we can just leave it there or calculate it. But that's not what we wanted. We found dv. We wanted the relative error. Relative error is dv divided by the volume. So what is the volume in between? Well, the volume is going to be between either the volume is 4 pi 4/3 pi r to the third power. That's the volume. So that's the volume, and that's the volume. It's the same at 4,000, right? So dv over v would be what we found in the previous slide, divided by volume. So we divide everything by volume. So the relative error with respect to the volume would be about 0.06, right, to the right and to the left, right? So so the relative error is 0.06, which we convert to percent would be 6%. So notice that the radius is off. If the radius is off by that much, then the volume will be off by 6%, right? By 6%. So that's the idea of finding the amount of error given the input error. Okay, so I'm going to continue in the next video on chapter 4. I'm going to leave this to be on that section. And I'm going to come back here and say bye to you, and take care of yourself and others. I'll see you in the next video.